So we continue this lesson with a couple more terms. So we can talk about an inscribed figure and circumscribed figures. And literally inscribed means a geometric figure inside another figure. The inside figure's vertices must all touch. And some really unique things will begin to happen. The reverse is a geometric figure drawn around another figure so that all the vertices of the inner figure are touching the outer figure. So here we have an inscribed polygon. Here we have a circumscribed polygon. We could also say this one is an inscribed circle, and this one is a circumscribed circle. So it really is about which figure you're trying to emphasize, but the properties of both can come into play. So if we look at a couple of examples, like this one, given the diagram, find the radius and the exact circumference. Well, at first glance, it doesn't seem like we know anything about the circle, but if we look carefully, we have this really interesting right triangle inside of our circle. And if we have a right triangle, we can use the Pythagorean theorem to find the hypotenuse, which also happens to be the diameter of our circle. So in this situation, the diameter squared is equal to 12 squared plus 10 squared. And when we work that out, we get the diameter squared is equal to 244. Take the square root of both sides. The diameter is the square root of 244, which is approximately, well, we won't round right now, diameter to radius. We have to cut it in half. And so if we have the square root of 244 divided by 2, we'll get our radius. Now, why wouldn't I take the square root earlier? Well, if I take the square root and I round, and then I divide by 2 and I round, I'm going to introduce more rounding error. So if I just put the square root of 44 divided by 2 in my calculator and round at the very end, I actually get a more accurate rounded answer estimation. And I'm going to get about 7.8 units. The exact circumference would be, remember, circumference is pi times diameter. So our diameter, square root of 244 times pi. Not a great answer. If we want to use the decimal approximation, it would be 15.6 pi. Typically, when you do exact answers, we would not have radicals and decimals, but it is kind of a shortcut to get where we want to go. In the next example, we're given a square, that's key. So all of those properties from chapter unit 4, quadrilaterals, that we know about squares, specifically right angles and 4 equal sides, with an inscribed circle. So find the diameter, find the radius, and the circumference again. If this length is 18, obviously this one is 18, but no matter where I go across my figure, it's going to be 18. And if I happen to go uniquely right there, that is also 18, and where I've drawn it, that is my diameter. Half of that is 9. My exact circumference is 18 pi units. And so knowing things about those circumscribed figures lets us know things about the inscribed figures. So it's a kind of cool way to think about the different figures. Another idea we can talk about with circles are central angles. And this is an angle with the vertex at the center and endpoints on the circle. And the cool thing is we will talk about the measure of a central angle, and the measure is equal to the angle. So when we talk about a minor arc, we're talking about a segment, a portion of the circle's outer rim. So a portion of even the circumference, if you kind of want to think about it that way. But minor means that it's less than 180, and we name with the endpoints. So much like a segment, except it's curved. So for example, in this circle X, we name circles by their center, in this circle X, arc AB is a minor arc, right here, from A to B. And the measure of that arc AB, is equal to its central angle, 82 degrees. Major arc is a segment along a circle, and it's greater than 180, but less than 360. In this case, though, we need to name with the endpoints and 1 point on the arc. And that's really that tells us what direction to go. So for example, in the circle above, if I do this arc ACB, it tells me A and B are the ends, but I have to go through C to get there so I know which direction to go. That matters because, again, if we are going to find the measure of arc ACB, all the way around a circle is 360, and so that is 360 minus 82, the one piece I didn't do. I did everything over here, and when I do that, I end up with it equaling 278. And so we can work our way around our circles. In this example, just like we have parts to whole with angles, we can use that parts to whole with angles and add them together in the same way for arcs. So the measure of arc AC, well, A to C is right here. This piece is 25. This piece is 90. And when I add them together, I end up with 115. If I go to look at the measure of A to E, this whole thing here has to be 90, so that means that this piece right here is 90 minus 25, because I'm not using that part, and that ends up being 65 degrees. The major arc AEC, so start at A, go in the direction of E, and stop at C. So I either need to add this and this, that would be 65 and 180, or I could take 360 and subtract that piece, same answer, and we end up with 245. So that's a way that we can use those arcs and angle measures. Another thing we can talk about is arc length. Now don't get arc measure confused with arc length. Arc length is what fraction, what portion of the circumference. Okay, so it's a measure of the circumference, and it's a fractional piece, because we're really going to talk about how long is this, and we need to know what fraction of the distance all the way around it is. So the way that arc length works, arc length is equal to the measure of the central angle divided by 360 times the circumference, which means the measure divided by 360 times pi diameter, fraction times a fraction, we make it over 1. Now let's break this down a little bit. This is your fraction of the circle. So that helps us see what portion of the circumference we are using. So how does this work in action? Find the arc length of W to Z right here. Its central angle is 46. So the arc length is 46 of 360. We're talking about 46 of 360 degrees. That's our fraction, times our diameter is 30 pi over 1. Now we can go ahead and use our algebra skills. Anything with a 0, 0 and 0 cancel. That's a factor of 10. 3 and 36 are going to cancel, leaving 12. 46 and 12 have a common factor of 2, 23 and 6. So when it's all said and done, my arc length is 23 pi over 6. You can leave it as that exact answer, or you could go to your calculator, take 23 times 6, hit equal, then divide by 6. Just be sure that you get these multiplied together before you do the division. This next example is missing some information. So we're going to find the radius if the arc length is 58.25 and the angle is 320. We need that piece. So again, plug in what you know, solve for what you don't. Remember, length is the measure of the angle divided by 360 times pi diameter. So I know arc length and I know my angle measure. So I have 58.25 is equal to 320 over 360 times pi d over 1. So now it just becomes a matter of undoing. How do I undo division by 360? Multiply both sides by 360. So those two will cancel, and that makes this 2,970 is equal to 320 pi d. Now you can divide both sides by 320 pi. Make sure you treat it as a single number and don't have an error in how you entered an order of operations error. So our diameter ends up being 20.86, which means our radius is 10.43. So hopefully that makes sense. This is the end of this video. One more short video should take care of it.